In this video, we are going to see how to use the general transformation function. So here, this is one way of defining the general transformation function that takes into account the possible transformations that we will see in this course. So different variables in this function represent different transformations, are there holding the place for different transformations. So like g of x would be the transform function, and it is equal to f of x with certain transformations applied to it. So here the d in this function is corresponds to vertical shifts up and down. So this is our vertical shifts. That's D. And then this x minus c here, that corresponds to our horizontal shifts, right and left. The b in the function corresponds to our horizontal scalings, and it can also be reflections across the y-axis. So like negative would be a reflection across the y-axis. So this could be horizontal scalings. Any horizontal scalings would change what B represents, and also reflections across the y-axis would change B. If we're reflecting across the y-axis, B would be multiplied by -1. Then A is our vertical scaling transformation. So A is where we place our vertical scaling. If we want to affect a vertical transformation scaling, then we would change A. This is also where we would do a reflection across the x-axis. So an x-axis reflection. So we would do multiply by -1, the A by -1 for a reflection across the x-axis, or to flip the graph over, basically, for the transformations. Okay, so keeping these things in mind, we're going to look at an example and making changes to the function based on what transformation we want to apply. So moving over here, so our function f of x is our original is x squared. And here's that general transformation function. And the transformation we want to do is we want to shift the function down 2 units. So how that changes the function is basically the new transformation function would be, what we're doing is a vertical shift. So we have our function and we're doing a vertical change. So we are affecting it with D somehow. So here, because it's down 2 units, we would be subtracting, we'd let D equal -2, so we'd be subtracting 2 from f of x. Whoops. To go down 2 units. Take the function down 2 units vertically, we would have to subtract 2 from every y value. So we subtract 2 from f of x. And since the function is x squared, basically we're saying x squared minus 2. If we want to shift up 2 units, same idea, except instead of -2, we're actually adding 2 to the function. So we would just be interested in the vertical shift again. Right? We'd just be interested in D this time, and we have that we're adding 2 because we're shifting up, a vertical shift up, so D would become +2, and we'd have x squared plus 2. To shift left 2 units, now it's a horizontal shift. So the part that we're interested in the general transformation function, what we're using is we have a horizontal shift, so f of x minus c is what our general function will look like. And we just have to change c because we're going left 2 units. We would be subtracting 2. So because we already have a minus there, what it ends up being is x plus 2. Subtract 2 and you have a minus, so you have a negative and a negative, which would make this x plus 2. Here in the function, but notation, and that would be x plus 2 squared. That's what the equation would look like, x plus 2 squared. Okay, if we want to reflect across the x-axis now, remember x-axis was the a part, it was the a in the general function. So what we're interested in is this a that's being multiplied by the function. And to reflect it across the x-axis, we would need to multiply by -1. And since there's no actual scaling going on, a is just 1. So we have negative f of x, just to reflect across the x-axis, which would be negative x squared. And if you think about it, based on what we learned about symmetry, that makes sense. When you want to reflect something, you multiply across the x-axis, you multiply the y value by a negative. Now, if we want to reflect across the y-axis, we take the function and we're going to keep b, because b was the part that was reflection across the y-axis. So we'll keep b as part of our transformation. We're not worried about x minus c because we're not doing a horizontal transformation. We're just doing a reflection across the y-axis. And again, there's no scaling. There's no horizontal scaling, so b would just be 1, and we'd multiply by negative for the reflection. So we'd have f of negative x, or negative x squared. Notice the difference between reflecting across the x-axis versus the y-axis. And across the y-axis, the negative is being squared, but across the x-axis, the negative is not squared. Here, you're making the x value negative, the input negative. Here, you're making the output negative to reflect across the x-axis, which makes sense also based on what we've learned about symmetry and reflecting points. Okay, so for a vertical scaling, now we're interested in a. A was the thing multiplied by the function on the outside for a vertical scaling, and it doesn't say, there's no other transformations going on. So it's a function of the form a times f of x for a vertical scaling. And in this case, we are stretching by a factor of 2. So we're multiplying the function by 2. So basically, we're saying 2 times x squared. The transform function in this case would be 2x squared. The 2 is not squared, just the x, because 2 is being multiplied by the function. It's not actually being plugged into the function. For a compression, we go the other way, and we, instead of multiplying by 2, if it's compressed by a half, we'd multiply by a half, or we're basically dividing by 2. So it's a vertical scaling, so a f of x, and now it's a half times f of x. So we get a half times x squared. So vertical scalings, it's something being multiplied by the output of the function. A horizontal scaling, on the other hand, will be something multiplied by the inside, by the x value, multiplying something by the x value. So here, for this horizontal compression, we are interested in a horizontal scaling, so that's b in the general function. So we'd have g of x, the transform function, equal to, there's no vertical scaling, so we don't keep a, there's a horizontal scaling, we keep b, there's no horizontal transformation, so we just say x, no vertical transformation. So here's what the function is going to look like for the transformation if there's just a horizontal scaling. And in this case, when you're doing a horizontal compression by a factor of 2, you're actually going to multiply x by a half instead of 2. So you'll have f of a half times x. So you'll get a half x squared as your function. You're multiplying a half by the input for horizontal scaling and compression. For the horizontal stretch, it's the same general function, fb of x, because that's the part that we are changing is what's being multiplied by x. And by a factor of a half, we would actually be multiplying the x value by 2 for a horizontal stretching. So it would be f of 2x, which is then 2x squared. Hopefully you're getting the idea, because now we're going to look at 2 examples with multiple transformations, so a little more complicated. So for these, like this first one, it says we want to shift up 3 units. So we've got a vertical shift, we've got a horizontal shift left 1 unit, reflecting across the x-axis, so, and a vertical compression by 5. So here, our general transformation function, we need a vertical scaling and a reflection. So we have a reflection across the x-axis. We have it doesn't say anything about a horizontal scaling, so we won't keep b, but we do have a horizontal shift. So we have to have our transformation in there for the horizontal shift, and we have a vertical shift. So this is the equation that we're going to use for our transformation. We're going to have a vertical scaling, we're going to have a horizontal shift, and we're going to have a vertical shift in our equation. So here, according to what it says, it's reflected across the x-axis, so a will be negative, and at the vertical compression by 5, so it would be multiplying by 5. Negative 5 times f of x, and shifting left 1 unit would be plus 1, x plus 1 for the shift, because you have minus c, so it would be minus negative 1, so you'd have plus 1 there. And a shift up 3 units would be adding 3 to the function. So this, with that original equation, would be negative 5 x plus 1 squared plus 3. There's the transformed equation. For this next one, this time we're shifting down 5 units, so we have a vertical transformation down, a horizontal compression by a factor of 4. So what we're interested in here is we've got, it doesn't say anything about a vertical scaling, so we won't keep a, but we do have a horizontal compression. So b, that's a scaling, so we keep b for a horizontal scaling. There's no horizontal shift, so we just put x there, and we have a vertical shift down. So this is what the general function looks like for these transformations. And we get, since our compression is a factor of 4, remember you have to multiply x by 1 over 4, x, and then we're shifting down, so it's negative 5 units. So here we get 1 over 4 x squared, if we plug it into that original function, x squared, minus 5. This would be the transformed equation based on these transformations.